Now that we understand the previous video with the introduction to extreme values and how the first and second derivative relate to the graph of a function, we can move on here and look at what the extreme values actually are. So this is something you'll see a lot on the AP and in your homework, is this concept of finding extreme values of the function, and a lot of problems where this will come up will also be optimization questions. So we'll want to make sure we really understand this. Now, luckily enough, if you understand derivatives, learning extreme values will not be too difficult. So extreme value is a pretty easy concept to understand right off the bat. Just by, I had made this example question here. This is what you'd expect in a homework question. Not too difficult, but we'll start out with a real question here. So let's get, I'll switch this to black here. Okay, so in this graph, we have some extreme values. We have what are called, we have what we could call local extreme values and global extreme values. So I'm going to go ahead and type this in here. Okay, so what's a local extreme value? When we look at this function, the two local extreme values I see are the one here and the one here. Actually, I'll change the color. It's a little hard to see. Okay, that's better. Right there and right there, we see local extremes. And here at the end, and here, actually this is not necessarily true. A global extreme, the global minimum will be the smallest value over the entire function, over the entire interval. So here this interval is -2 to 2. So the global minimum in this cutoff is over here at x equals -2, and the global maximum is over here. But sometimes it's not enough to figure out what these values are, and we have to figure out what these are. These ones in the middle. These are clearly critical points where we hit this local maximum value and start going down again, or this local minimum value before we start going up again. Obviously, these two values are not the highest or the lowest over the entire domain here, but they're still really important because this is we'll want to solve for these values if we're doing optimization. Now, what you'll see is they don't necessarily fall in an exact number. Because we set the domain here from -2 to 2, we can easily plug in 2 here or -2 here to get this value, to get the value of y. But here this doesn't fall exactly on a specific x value, or not necessarily. So we'll have to use calculus to figure out the x and y values of these points. And so how do we do this? We have to do this by using derivatives. So we're going to take advantage of what we've learned over all the videos so far with derivatives and say that we know that the derivative at this point, at this critical point, is this straight line, because as it changes direction, it's at that exact point where the slope of the line is 0. The slope of the tangent line, sorry. Same thing here. There we go, perfect. Now, if the slopes of the tangent lines here are 0, then that means that, well, okay, I gotta change the color. Okay, that the derivative equals 0 at the critical points. So you might say, well, now we've made this observation, but how does this help us? Like, what do we gain from knowing that the derivative is 0 at these points? Well, all this means is we can easily figure out the value of these points by taking the derivative of this function and then setting it to 0. So the derivative of the function, let's move this. The derivative of our example here, you should already be able to do pretty easily if you've made it this far, is 3x squared minus 2. 4 goes away. So now this is the derivative for the overall function. So to find these critical points, we're going to set it to 0. So this means we'll go 3x squared minus 2 equals 0. Doing some algebra, we move the 2 over, get 3x squared equals 2. X squared equals 2/3. And then finally, x equals the square root of 2/3. And because we took the square root, we're going to have to give a plus and minus out front here. And so now we can see these values here. We've solved for them really easily using derivatives. But how hard would this have been using pre-calculus or some other method from algebra? Really, calculus is the best way to solve these types of questions. This square root of 2/3 is not a clear answer, but is not obvious from the graph. And it's not an easy whole number or an easy fraction to come up with. So that's the power of using calculus to give us these answers right away. And the nice thing about calculus is it's actually easier to solve questions like this once you understand derivatives, because now there's not just some weird trick that you have to memorize. As long as you understand that the derivative is 0 at these 2 points, then you're fine. So let's say we want to clarify. This is the maximum here, and this is the minimum. But what if I hid this graph from you? And so I'm going to do this. I'm going to take the graph and move it down here so we can't see it. Okay, so say you were doing this question that's asking where the local extremes are, where it changes direction with this function. We figured this out using only this function here. We didn't have to look at the graph, although if we looked at the graph we could see that this answer makes sense. But now what if they're asking you which one's the minimum is and which is the maximum? So I'll put this here. Whoop. Sorry, my typing's a little off there. Which is minimum and which is maximum? So we have two values here. We have radical 2/3 and negative radical 2/3. So if you remember back to our previous video, the introduction to extreme values, we said that we'll have a maximum, or that the graph will look like this. Here, actually, to make this explanation easier, I'll bring it back. So, we brought it back. Which is the maximum and which is the minimum of these two values? We can look at the graph and say, oh, the positive radical 2/3 is obviously the minimum, the local minimum here. And the negative value is where it reaches that local maximum. But how do we use this information? How do we find this out without looking at the graph? And what if it's a really complex question and you're on a test and this is all you have right here? The way to do this is to take these two values and plug them into the second derivative. Now, let's just go ahead and take the second derivative here. I'm going to make a copy quickly of this, bring it over here. So here's our derivative. So This is the second derivative notation. Might be a little awkward. I don't think I've written this yet, but the second derivative is, I can bring this down, the 6x. 2 goes away. So we're left with 6x. So now, copy this one over. We've got 6x. So let's plug it in. We actually don't even have to plug it in. We can see right away that if we take this value and plug it in here, then the answer is going to be positive. And if we take this value and plug it into the second derivative, then we're going to get a negative answer. So if we get a positive value out of the second derivative being positive means that we're accelerating upwards. The second derivative being positive means that we're going, even if we're going downwards, it's happening less and less until we reach a point, and then it starts going up and accelerating upwards. You can see that it's moving upwards faster and faster. So because this is positive, we know that this value has to be associated with that minimum. And then this value, because we're getting a negative second derivative, means that the acceleration is negative here. So we're going upwards, upwards, upwards at a slower and slower rate, and then we hit zero velocity, start accelerating downwards. At least this is the easiest way to think of it, I think. So if this doesn't make sense, just remember, I'll make a little list here, how you do these extreme value questions. So I'll clean up here, and we'll just go over. How do you find local extremes? So take the first derivative and I'll move this over a bit and set it equal to 0. Set it equal to 0 and solve. And then plug in results on the graph, or we'll say this. Look at results on the graph, or plug into second derivative. Positive result equals local minimum. Negative result equals local maximum. So to sum it up, here are the steps to solve these extreme value questions. I'll kind of have this indented here. So taking the first derivative and setting it equal to 0 and solving, this gives you these values. Switch to black, maybe that'll be easier. Or let's do red, okay. This gives you these values. It tells you where they are on the graph, so you can find those points. And then, using the second derivative, you can figure out whether these are at the tippy top of a local curve here or at the bottom of the local curve. So, in the next video, we'll come back to an example like this, but something more of a real-world questions where we're doing optimization, and we have to look at both the global minimum and maximum and the local ones. So this came up on the AP exam. That's something you'll really want to understand. So be sure to see me in the next video. Until then, thanks for watching, and goodbye.